we had the general addition and the addition rule for disjoint events. So basically, though, if you look at both of those, they were the probability of E or F. So when you're seeing an or statement, that's when we ended up adding probabilities together. We had two separate cases, one where it was mutually exclusive and one where it was not. So make sure you know what that means. Mutually exclusive. Or another word for that is disjoint. What does that mean if things are mutually exclusive or disjoint?
It can be one thing and it can't be both things.
Right. They can't both happen at the same time. So basically, it means probability of both things happening is what? 0. So that was the difference when we had the two rules. We had to look at whether they were disjoint or not. If they weren't, there was overlap, so we had to subtract off what we overcounted when we put those together. So today, we are going to be talking about and, the probability of A and B happening. So when I'm doing an or, we end up adding those little individual probabilities. When we're looking for an and statement, any guesses what we'll do? We actually end up multiplying the probabilities. So moving forward, when we're trying to figure out what to do when we see an or, that's kind of a clue that we need to add. When we see an and, we will end up multiplying things. We do have a couple terms that we need to go through, just like we had an or rule for when things were mutually exclusive and not. When we're talking about and, we have to worry about independent versus dependent. So first, let's write down those definitions, and then I'm going to talk about what they mean and how they relate to us. So independent, the occurrence of one does not affect the probability of the other. And dependent, it does affect. So I'll let you write it and then I'll talk. So independent events are completely unrelated. It would be like if I said the probability of you wearing a red sweatshirt and it raining today. Do those things have anything to do with one another? No. But if I said the probability of you wearing rain boots and it raining today, do those have something to do with one another? Yes, because you are going to be more likely to wear rain boots on a day when it's raining. Okay, so it doesn't necessarily mean one causes another. It didn't rain because I wore the boots, but the probabilities change if you know that one is going to happen. So let's just take a look at a few scenarios and see if we can decide if these are independent or dependent. So suppose we're going to draw a card from a deck of cards and then roll a die. So the events draw a heart and roll an even number. Would those be independent or dependent? Yeah. Does the card I draw from the deck have anything to do with the number I roll on my die? No, they are totally separate. So these are independent events. Even if I roll an even number, that does not change the probability that I get a heart when I draw a card. All right. Suppose two 40-year-old women who live in the United States are randomly selected. The events woman 1 survives the year and woman 2 survives the year. Do those have anything to do with one another? If I just take two random people in the United States. No. Does one person living change the probability that the other one lives? No. Okay, so those would be independent. C. So I still have my two 40-year-old women, but they live in the same apartment complex. So the events woman 1 survives the year and woman 2 survives the year. Would those be independent or dependent? Dependent. Why? Exactly. Could something happen that could affect both of them? They are living in the same area. So there could be a gas leak there. There could be a fire there. They could live in Florida. They could So they could be impacted by a hurricane. There could be, you know, a COVID outbreak or something. So things could happen. Now, does that mean it's if one of them dies, the other one is going to die? No, but we're just saying there is a chance, albeit maybe small, that something could happen to both of them and be related. Okay, so these would be dependent events. All right, so we have our multiplication rules. Today we are only going to talk about independent events. So we need to know the difference between independent and dependent. We are not going to find the probability for dependent events until next week. So today we're focusing only on this one, which is on your formula sheet. You do have to flip. We're now on the second page. So the first thing on the second page is our complement, which we talked about yesterday, 1 minus. And this is right underneath that, the multiplication rule for independent events. So if E and F are completely independent, they have nothing to do with each other, then the probability of E and F happening, we said and means multiply, so all you have to do is the probability of E times the probability of F. And we could extend that. I only put it for 2 events, but it could be as many as we wanted as long as they're independent. So we could just keep multiplying those things. Okay. So the probability that a randomly selected female aged 60 years old will survive the year is 99.186%. What's the probability that 2 randomly selected 6-year-old females will survive? So I'm asking you for the probability the first survives and the second survives. All right, are these 2 women independent? Yes, I didn't say they're sisters or they live in the same place or they work the same job. So they are totally unrelated to one another. So all we have to do is multiply their individual probabilities. So what's the probability that the first one survives? Times the probability the second one survives. So we get 0.9838. Or there's a 98.38% chance both of these women will survive the year. What's the probability that 4 women survive the year? What would we do? Keep multiplying. You have to multiply it 4 times, or you could just do it to the 4th power. All right, so let's figure that out. I'm going to add another question here. So we found the probability that all 4 live just by multiplying that probability 4 times, or doing it to the 4th power. What's the probability that at least one of the 4 does not survive? So there are several ways of doing it. You know, at least one of the 4, so we could like find every combination. So the first one doesn't and the next 3 do, or the second one doesn't and the rest do, or the first and second don't and the third and fourth do. But that's a lot of combinations, right? But if we recognize at least one not surviving. Isn't that the opposite of everybody surviving? So these are complements. And we know that from yesterday, to find the probability of a complement, you just do 1 minus. So all we have to do is 1 minus the probability that they all survive. And we found that probability in the previous question, so 1 minus. So does everybody understand why we're doing that 1 minus there? It's only because these two things are complements. Together, they give us every possibility. Either everybody survives or they don't all survive. Those are the only two options there. I didn't ask what's the probability that all 4 don't survive. That would be a different question. Then they would not be opposites. But in this case, they are. Is that all right? So why don't you guys do this one? Probability that at least one of 500 randomly selected females will die. Okay, I don't want to go through and calculate all those probabilities. It could be the first one dies and the other 499 live, or the second one dies and the other. I mean, that's going to take me all day. But we know this is the opposite of them all surviving. So we just have to do 1 minus the probability that they all survive. Okay, the probability of one person surviving is 0.99186. So to get the probability that 500 of them survive, you would do to the 500th power. You'd have to multiply it 500 times. And so we get 0.9832. There's a 98.32% chance that somebody does not live the entire year. Is that okay? All right. Let's look at this one. A manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers will actually use the equipment in the first year after it's purchased. If there is a 1-year warranty on the equipment, what proportion of the customers will actually make a valid warranty claim? So what conditions have to happen for somebody to make a valid claim? It has to be defective, and they have to know it's defective, right? If they don't ever use their equipment, are they going to know there's something wrong with it? No. So in order to have a claim, we need to find that the probability is defective and they actually use it. All right, are those things independent or dependent? Independent. We know that some of our equipment doesn't work. Now, does that mean that if I ship one to Eli, does that change the probability that he's going to try to use it if it works or not? No. It changes the probability if he actually can use it. But if he's going to try it out or not, that has nothing to do with whether or not the equipment works. So these are independent. So all we have to do is the probability that's defective, and means multiply, so times the probability that you actually try to use it. So what's the probability of being defective? 0.1. What's the probability you try to use it? 0.3, only 30%. And so you get 0.03. So they are only going to have to replace or have a valid claim 3% of the time. Is that unusual? What's unusual?
Less than 5.
Less than 5%. So would it be unusual for them to actually have to have a warranty claim? Yes, because the probability is less than 5%. All right, questions? So just kind of recapping everything we know about probabilities so far. Okay, you guys don't necessarily have to write this all down. We have it all written down in our notes, but we're just kind of recapping. Anytime I find a probability, it has to fall between 0 and 1. If you add up every possible probability for a scenario, it always has to add up to 1. It's 100%. Okay, then yesterday we talked about the OR probabilities. OR means add. So if they're disjoint, which means they can't both happen, you just add their individual probabilities. If they are not, you have to add them up and subtract off the overlap because you double counted some people. What does this E with a C represent? The complement. It's the opposite. So the total opposite of something, you just do 1 minus your probability. And then today we learned that if they are independent, so we only know how to do ands for independent right now, all we have to do is multiply their individual probabilities. Okay? So I am done. I want you guys to do your homework. Same rules as the last few days apply. So a lot of you say find and interpret the probability. You don't have to do the interpretation unless that's the only thing the question asks for. Like I'm pretty sure question number 20 has an A, B, and C, and part C is interpret the probability in A. So if that's the only thing the question asks for, interpret, but otherwise you do not have to do the interpretation.